Dear students, today we'll see what do we mean by RC differentiator circuit, which is used, which is made by using a resistor and a capacitor. It is also called as a passive differentiator because it is made up of R and C. There is no any active element which can amplify it. Okay. So here, RC differentiator will be our topic. Now, before this, we had seen what was an RC integrator circuit. Okay, so in RC integrator, we saw that our R was in series with the input and C was parallel to the output. Okay, so it was something like this. R was with the input in series with the input. So here you are giving the input. Okay, and then capacitor we used to put here. This is the capacitor and output. If you take here, okay, then it will be called as integrator circuit. This is what we have seen for integrator. Now, in place of this DC voltage, if you give a sine wave, and same RNC circuit, okay, RNC circuit, then this will act as a low pass filter. This will act as a low pass filter. This was your gain. This will act as a low pass filter. Okay. Now, similarly, when we speak about differentiator, the position of R and C will be exchanged. So here, if you take C and then R here for the output, so through C you are going to give the input, okay, and across R you are going to take the output. If you do this, then it will be called as differentiator. It will be called as differentiator. Similarly, in place of DC supply, if you give a sine wave of various frequencies, then the same combination can act as a high pass filter. High pass filter. Now, this is what we are going to see. And in this presentation today, we are going to see what is RC differentiator. So if you see the basic definition of RC differentiator, the passive RC differentiator is a series connected RC network that produces an output signal which corresponds to the mathematical process of differentiation. That means this circuit is going to perform a mathematical differentiation process, and that is why it is called as a differentiator. So here you can see the circuit of a differentiator where you are having a capacitor in series with the input. So here you can see this is a capacitor in series with the input. The voltage across the capacitor can be named as VC, and then here is your resistance which is across, and across that resistance you are going to take the output voltage V out, and this simple combination of C and R in this way will work as a differentiator. Okay, now here how you can prove that it is mathematically working as differentiator. Okay, now if you refer this circuit, now here you can see that your C is in series and the voltage across C you can name it as VC. Okay, and the voltage across R is VR, which is nothing but V out. Okay, now in this case, first we will start our derivation by remembering that we know the charge in a capacitor Q is equal to capacitance into the voltage across it. Capacitance into the voltage across it. That is Q is equal to CVC. This is a fundamental basic relationship when we study about capacitor. Then we know that in a capacitor, okay, the current which is going to flow is the rate of change of the charge dq by dt. Okay. Now, because q is equal to cvc, we can write this as d cvc by dt. Okay. Now here, the reactance of capacitor, that is the opposition to the flow of current produced by the capacitor, which is denoted as a xc, is much larger than R. Is much larger than R. So in that case, the voltage across the capacitor will be approximately equal to the input voltage, because all the voltage will come across the capacitor and very negligible voltage will come across the resistor. Okay, so Vc is equal to Vin. Okay, now if you take the relationship of I, we know that I is equal to dCVc by dt from this equation. Okay, now this is nothing but, when you take Vc, it is nothing but Vin, as we have proved here. Vc is approximately equal to Vin, so this you can write as C d Vin upon dt. Okay, now this C d Vin upon dt. Okay, so Vin upon dt and C, that is the relationship of the voltage across the capacitors. Now this will be equal to the output voltage upon resistance R. Okay. Now we have to concentrate on this relationship. We have to concentrate on this relationship. Now if you see this relationship, then from that relationship it is V naught, which is equal to, okay, RC dV in by dt. Okay. That is, in this expression, V naught is proportional to derivative of input with respect to t. Okay, so if you do dv in by dt, that is rate of change of v in with respect to with respect to t, then that will be your output voltage, and therefore this shows that the output voltage is the differentiation or a mathematical differentiation of the input. This is what we have proved, that the circuit with C in series with the input and R across which you are going to take the output will act as a differentiator. So this is a passive RC differentiator. Now here, if you see, if you are giving the input as a square wave, okay, if you're giving the input as a square wave, the output will be spikes. Okay, the output will be spikes, and the width of the spikes depends upon the uh, product of C and R. Okay, so here we have taken C as 1 microfarad and R as 1 kilo ohm. Now, in this case, this is the time period 20 millisecond of the on and off. This is on and off. So whenever it is on, it is going to give you a spike here, and whenever it is off, it is going to give an inverted spike here. Okay, so this is how you are going to get spike if the input is a square wave. Now here you can see the different outputs. Now the input we have shown in blue here on top, which is T on, T off. This is your input. Again T on, again T off. Okay, again T on. So this is the input. This is the time period. Okay. Now here, if you see, if you keep the RC time constant 10 times, 10 times RC, okay, then the output will be like this. It is not spikes now. It is somewhat like, it will have its own charging and discharging of capacitor, but it is having a width also. There is no spike type. Okay. Now, if you want to reduce that, we will reduce it to one time RC. So here you can see it is one time RC. Then there is a difference between this waveform and this waveform. If that RC becomes 0.5 RC, then there is a difference between this and this. You can see that the discharging part is going little lower. Now, if you take zero point 0.1 RC, then you can see it is spikes. It is spikes. When the input is positive on, it is positive spike. When the input is negative, it is negative spike. And you can see spikes properly if your RC multiplication, that is product of RC, is taken as 0.1 RC. Now for various inputs, what will be the output of the differentiator circuit? So here, if you see, if the input is sine wave, the output is cosine wave. In the first case, when the input is sine wave, the output is cosine wave. If the input is square wave, the output is spikes. If the input is triangular wave, the output is square wave. This is just opposite to integrator. Okay. Now, if you see the basic circuit, of RC or differentiator, then this circuit can also act as a high pass filter because say at the input if you are applying a sine wave, sine wave here, whose frequency will vary, whose frequency here will vary between some range, okay, between some range, this input frequency f in is going to vary, okay. Now, in that range of frequency, okay, the higher frequencies are passed by the capacitor because the reactance of capacitor Xc is equal to 1 by 2 pi Fc. So it is inversely proportional to the frequency. So if the frequency is high, the reactance is less, it can pass and go to the output. Okay. But if the frequency is less, the reactance is more, it will block it. And anyway, if it is passing through it, that low frequency, it will go through this resistor and it will go to the ground. So only high frequencies are going to pass here. Now that high frequencies which are going to pass also depend on a cutoff frequency Fc, which depends on the value of C and R. So if you see the graph of gain versus frequency here, say this is y-axis is gain and x-axis is frequency, then you will get something graph like this. Okay, so here it is stop band. This is your cutoff frequency and this is your pass band. So you're going to pass all the frequencies above the cutoff frequency and you're going to stop all the frequencies below the cutoff frequency. So this is how a RC differentiator circuit can also act as a high pass filter. Now if you see some applications of differentiator, the differentiator circuit is essentially a high pass filter. It can generate a square wave from a triangular wave input and produce alternating direction voltage spikes when a square wave is applied. That we have seen, if you apply a square wave, the output will be spikes. In ideal cases, a differentiator reverses the effects of an integrator, so it is just working as opposite of integrator. They are most commonly used in wave shaping circuits to detect high frequency components in an input signal. Differentiators are an important part of electronic analog computers, analog PID controllers. They are also used in frequency modulators as a rate of change detectors. So these are few applications what we can note about a passive differentiator. It is RC differentiator. Okay. Thank you, students.